Okay, for this third question, we have a rational function, and because it's a rational function, it's probably going to have some asymptotes. So before we draw, we need to figure out first the x and y intercepts, horizontal asymptotes, vertical asymptotes, and then after that you need to figure out the derivative and the second derivative, and using those values you should be able to sketch. Okay? All right, so solution first, let's figure out what happens when x is equal to 0. You get y equals to 2 times negative 9 over negative 4, which is 9 over 2. So 0, 9 over 2 will be the y-intercept. Now what would you get if you set y as 0? That is 0 equals to 2 times x squared minus 9 over x squared minus 4. For a fraction to become 0, its numerator has to be 0. Okay? If the numerator is non-zero, then there's no way a fraction can be equal to 0. So you can just say 0 is the numerator, and you can divide both sides by 2, and then move the 9 on this side, and you get x squared, x equals to plus minus 3. So you have 2 x-intercepts that way. Now for the vertical asymptote, what do? You remember? Set the denominator equal to 0. This is the denominator. I should write it here. So we set the denominator equal to 0, and you get x equals to plus or minus 2. Now for the horizontal asymptote, you have to send limit x going to infinity and also negative infinity, but in that case, in general, if you have a polynomial over polynomial, then as long as the horizontal converges to a single value, they're going to converge to the same value. So that's something good to know, so that you don't have to do it. If the limit doesn't converge to a finite value, but it goes to positive infinity or something like that, then the two limits may not be the same. So this limit is, as I explained yesterday, it only concerns the big pairs when x goes to infinity. When x is a really large number, these are very small compared to that large x, so only these matter. And when you simplify this, that's just 2, so the value of the limit is 2. And because it converges to a single value, you can pretty much see that it's going to be the same value if you send x to negative infinity. The first example that we did today had a different limit going right and left. That was because it had an exponential function involved. Right? But if you don't have exponential functions, if it's just polynomial over polynomial, then the two limits are equal. So we can save time by not considering the other one. So the horizontal asymptote is y equals to 2. Okay, so we got the intercepts and the asymptotes. Now let's find out y prime. To find y prime, we need to use the quotient rule. So you have to differentiate the top times the bottom minus differentiating the bottom times the top over the bottom squared. This differentiates to 2x times 2, that's 4x, x squared minus 4, minus, differentiates to 2x times 2, that's again 4x, times x squared minus 9, over x squared minus 4 squared. And then when simplifying, it's good to factor the ones that are common. So I'm going to factor the 4x out, and that's x squared minus 4 minus x squared minus 9 over x squared minus 4 squared. X squared minus x squared cancels. Negative 4 minus negative 9, that's plus 9 minus 4, 5. So you end up with 20 times x over x squared minus 4 squared. Now, what are we interested in now? We are only interested in the sign of y prime. And as you can see, anything squared is always positive, so we don't have to worry about the bottom. 20 is a positive number, so the only thing that does change sign is x. When is x equal to 0? When x is equal to 0. If x is positive, the entire thing is positive. If x is negative, the entire thing is negative. So you can see that for y prime, it's 0 at 0, and it's plus here and minus there. All right, to give room for y double prime, we'll have to erase this. So let me erase the calculation I did for y prime. Let's put down 20x over x squared minus 4 squared. And then just make a note that y prime is negative before and positive after 0. Let's erase everything. Okay, now the second derivative. Now, sometimes it does happen. Sometimes when you try to use the quotient rule, you can forget it. You can suddenly forget the quotient rule, and you can be in a state of panic. But there's no need to worry. You can always use the product rule and the chain rule together in place of the quotient rule. And let me show you how that can be done. So you can rewrite 20x divided by x squared minus 4 squared as x squared minus 4 to what power? Negative 2 power. So you can instead differentiate this one. And it's especially effective when your denominator is not a simple one, but it has a power of 2 or it has a square root. In those cases, actually trying to differentiate using the product rule and the chain rule is not that bad. It's actually very effective. Okay? So let me show you how this one is done. You differentiate the first one, leave the second one without doing anything. Plus, you leave the first one, but then differentiate the second one. Derivative of 20x is just 20. And then differentiating this, now you need the chain rule, but hopefully you practiced a lot with the chain rule that this is like an easy question to change. The negative 2 comes in front. Subtract 1, that's negative 3. Pull the inside out and differentiate, that's 2x. And then you have to go back to the fraction form, because, I mean, if this was simply a differentiation question, if the question was find the derivative of this function, then you can just stop here. That'll be good enough. But since we have to use this for figuring out the sign of the second derivative, we have to simplify this further. So you have to go back to the fractional form. So negative power means positive power with the denominator, placed in the denominator. Same thing here. Let's see, negative 2 times 2 times 20, that's 4 times 20, that's 80, right? It's negative 80x divided by x squared minus 4 cubed. And then, in order to make common denominators, you need to put x squared minus 4. You have to multiply x squared minus 4 top and bottom, so that they have common denominators. And therefore, the first one is 20 times x squared minus 4 minus 80x. And that will be 20x squared minus 80x minus 80 over x squared minus 4 cubed. Let me check.
Shouldn't that be 80x squared?
Oh yeah, that's fine, that's fine. There was an x that I didn't see. So it should be x squared. Okay, so that changes the answer. That's 20x squared minus 80x squared, that's negative 60x squared minus 80. So you can get the same answer by applying the quotient rule. Let's factor out the negative 20. So you have 3x squared plus 4 over x squared minus 1. So applying the quotient rule or doing this method, that's what you get for y double prime. Okay. For this one, this is always negative, this is always positive because it's x squared, right? So the only time that it changes sign is when this changes sign. Now when does this change sign? When does this equal to 0? 2 or negative 2, right? Now it's a little confusing to just go by this sign because of this minus. So let's just first try the points where this thing becomes 0. So at negative 2 and 2, this thing downstairs will become 0. And we will pick test points between, after, and then before. Plug these values into the y double prime. And you're going to get, if you plug in 0, that's negative over negative, so it'll be positive. If you plug in 3, that's 9 minus 4, that's positive. This is negative, that's always positive. Negative divided by positive, that's negative. And if you plug in negative 3, it's still the same thing because it's a 9. So it'll be a negative before. Okay, so we know that before 0, the graph will be going down, and after 0, the graph increases. But there's also something happening at 2 and negative 2 because the concavity changes. Now there's a nice way to put everything as a table, so let me use the book to give you this table. Okay, before negative 2, before negative 2, F prime is negative because it's on the negative side. F double prime is before negative 2, what is it?
Negative.
Negative, right? So what's the characteristic of the function f? This means it's decreasing. And this means, I'll just put C concave up. Now how would you make the shape? It's decreasing. Concave up means you're pushing this from above. Oh yes, sorry. Concave down. Okay. So concave down means you're pushing this from below. So which way would it bend? It's going to bend like this. Right? So that's the way it's going to bend. And at x equal to negative 2, we have the vertical asymptote. All these are undefined. That was what we figured out. Also, we have another one at x equal to positive 2. Now, between negative 2 to 0, f prime is still negative, f double prime is positive. And what's the significance of 0? Before 0 it goes down, and after 0 it goes up. So what kind of value is 0? It decreased and then increased. What is this point? Relative minimum. So the characteristic is relative minimum. And if, oh no. 0 is the relative minimum, sorry. This is just decreasing concave up. And x equal to 0 gives you relative minimum. And between 0 to 2 will be positive, and x equals to 2 is a vertical asymptote. And after 2, this will be positive and then negative. So this, I'm running out of time, so let me do this quickly. This is increasing, concave down. This is increasing, concave up. And this will be a vertical asymptote because it's all undefined. All right, so putting all this together, this is the way we can draw the graph. And by the way, on the exam, because all this takes too much time, you may be given just this much, and not this part. You may have to fill this in, and from this you can draw the graph. There are ways to take this entire problem in many parts, so that it can fit in an hourly exam. Okay? All right, so first, at x equals to 2, you have a vertical asymptote. X equals to negative 2, you have a vertical asymptote. 3, negative 3, you have a y x-intercept. 9 over 2, you have a y-intercept. And then it has to pass through in this manner because that's the way it's going to bend. Right? Now, I didn't fill this in, but you can pretty much see that before 0, it has to bend this way. After 0, it has to bend that way. And it has to be this way. So that's the graph. Oh, by the way, this is a little misleading because I forgot to put the horizontal asymptote at 2, so it has to be this way. Okay, so that takes everything into account. Horizontal asymptote, 2 vertical asymptote. This is the relative minimum. Is there an inflection point? There's no inflection point. I mean, there is a change in concavity, but it's not a point on the graph, so this graph doesn't have any inflection point. It doesn't have any relative maximum. It only has one relative minimum, and that's the